for this month's NCS 2030 webinar. And this month, Daniel Kiss is here to speak to us, and I will send it over to you. So thank you all. And all right, Daniel.
Okay, hello everyone. Once again, I'm terribly sorry for the delay, and I will talk about fault reactivation and induced seismicity and modeling approaches of these problems. Yes, so first of all, why fault stability or induced seismicity matters? There are lots of underground processes which involve fluid injection, so you can think of underground storage. The most famous one would be CCS. It could be wastewater, waste products. Often fluid injection is used for geothermal field development or enhanced oil recovery. And whenever we inject fluid underground, then that means that locally we have to raise the fluid pressure. And as you can see here in this cartoon, you have an injection well, you inject fluids, increase the pressure, and this can induce all sorts of deformations. So due to pore elasticity, the reservoir where the pressure is increasing would swell. This can create some stresses in the reservoir, also in the overburden, in the base rock. And in some cases, when fluids lubricate pre-existing faults, it could induce seismicity, which is, of course, of great importance if you live nearby. Same for surface deformation. So due to differential compaction or decompaction, in some cases, a significant surface deformation can be a problem. And we should always be wary of leakage and contamination. So, for example, if we want to store waste products, we would like to keep them at the designated storage formation, and we would like them to stay there. Yes. So very quickly, how fluid-induced fracturing works. So we have the fluid injection, we increase the pore pressure. This can result in differential decompaction. This would increase, this differential deformation would increase differential stresses. And at the same time, you can reduce the effective pressure. And just a quick reminder, most of you probably have seen these Mohr circle diagrams. This is the standard Mohr-Coulomb yield criterion, where you would have yield shear strengths, which would be proportional to normal stress on the fault. And according to Terzagh's principle, whenever we have fluid injection, then this normal stress here would be modified by the fluid pressure. So by increasing the fluid pressure, we in a way move this Mohr circle closer to the 0, 0 axis. And whenever we touch this yield surface, we would induce failure. So this is the simplest way how fluid-induced fracturing happens. But there are lots of questions. What happens after the initiation of fracturing? What is the seismicity pattern that we should expect? What is the magnitude that we should expect? What sort of deformation would this result in? Are we going to see a differential uplift or subsidence on the surface or not? These are all very relevant questions we cannot answer with simple Mohr-Coulomb analysis. And then what we will do to try to quantify this is hydromechanical numerical modeling. And why we need numerical modeling? It's very simple. The geometry and the physics is just too complex to do everything on a piece of paper. Therefore, we need numerical modeling. And then we have the hope to understand how this physical system works. So a little bit about the relationship between fracturing and seismicity. So here are two figures from studies related to breakouts. In this case here, you see data from a borehole breakout where microseismicity was used as a precursor to map the future fracture planes that then resulted in the breakout. And here you can see a study relating tunnel boring with the microseismicity and tunnel breakouts. So in engineering applications, it's quite well established that microseismicity is a good precursor of any sort of fracturing. And then this fracturing, microfracturing, will then be the place where macro scale brittle deformation happens later on. You can see the same in the rock deformation laboratory. So if you monitor acoustic emissions in these apparatuses, then you can often very nicely map fractures that later on will also be visible on the macro scale on the sample. And essentially, the idea, this was the inspiration for developing a method to calculate something that is called the seismic moment tensor. This is essentially what seismologists would reconstruct using seismic data and calculate it from plastic strain. So plastic strain is something that we can quantify in our numerical models, and it would be representative of brittle deformation. So I know the word plastic is a little bit controversial, because if you work in rock mechanics, then often plastic is everything that is continuous smooth deformation. From our point of view, from mathematical point of view, we call everything plastic whenever deformation happens at a given yield strength. And then we have difference between plasticity and viscosity. That would be more standard creep mechanisms. So long story short, in 2021, Alexander Minakov and Victoria Yarushina established methodology to reconstruct the seismic moment tensor from the numerical data that we obtained from two-phase elastoplastic finite element models. And this way, we have something, some model output that is very easily comparable to observables gathered from the field. A little bit about the model itself, the numerical model. So we solve essentially four conservation equations. So we solve for conservation of mass in both the solid and the fluid phase. And we also solve for conservation of momentum in the two phases. So in the solid, this would be standard solid mechanics. And in the fluid, it would be classical Darcy flow. And we investigate the coupled effects of these two different types of flow. And to link it all together, we use a porosity evolution equation, and we have porosity-dependent material parameters. So for example, permeability, but often, for example, the elastic parameters would be a function of porosity. And it means as the porosity changes from time to time, time step to time step, we also change all the parameters in the model. So it's a highly nonlinear problem. So this is just a quick reminder of the poroelastic bulk rheology that we use. This is pretty much standard in geomechanics. What's really important is that if you want to quantify compaction or decompaction and fluid increment, you have to know both how the confining pressure changes and the fluid pressure changes. So we don't have just single equations that can describe this, but we have this kind of matrix dependency. And all the parameters you can get from standard rock deformation apparatus. Then we take it a step further than poroelasticity, because it's quite possible to reach conditions where you don't only have elastic deformation that is fully recoverable, but we also have permanent deformation, which could be fracturing. It also could be creep. So imagine having a weak shale layer somewhere in your reservoir. You can have essentially viscous deformation on this horizon. Or if you have fracturing locally, that would be the plasticity. And the way we describe this in geomechanical modeling would be a poro-viscoelastoplastic model. You can see a sketch here, and we would have complicated plastic yield surfaces. Here again, I don't want to go further. It's just want to point out that it's again strongly nonlinear problem. And the way we try to deal with these strong nonlinearities is to use a novel computing strategy that is quite different from all the traditional methods. So we use a method that is called the pseudo-transient method, which today I don't want to go into details, but the main points would be that it's something that is called a matrix-free method, and it's very well suited for implementation on GPUs. This is because it's essentially a parallel algorithm. It's while the traditional algorithms that are mostly used are very difficult to parallelize, this algorithm is very easy to parallelize. And thanks to a novel computing programming language called Julia, and this package, if you are interested, parallel stencil, it's very easy nowadays to write GPU codes. So here you can see a code example for 3D heat conduction. You can do the whole thing in just about 3 lines. So to give you an idea. So it's very approachable to do it for every new problem, to write a new code. So why we also want to use GPUs? It's because probably you heard about it. If you compare it to CPUs, as long as you have to deal with a parallel problem, GPUs are just better. They are more cost efficient, they are more power efficient, they are faster. So as long as the algorithm is parallel, there is the only reason would be not to use a GPU algorithm is if you have already a legacy CPU algorithm and you don't want to spend the time to develop a new GPU algorithm. And a few extra advantages would be that it's actually, with using these new programming tools, it's actually very easy to write GPU code. So it's much more transparent, much more accessible. So hopefully there would be lots of independent teams in the future who can cross-check the work, and this way knowledge can be passed down to the next scientific generation. Okay, so why this all matters for reservoir modeling? And the main reason here is twofold. One is we need high resolution for some problems. So for example, here you can see a reservoir model with a fault cross-cutting this sequence. And the scale of the fault here, you can see it's 1 meter, 40 centimeters, 1 meter, so about 2.5 meters for the entire damage zone. And you have many kilometers of formations. So to resolve this kind of heterogeneities, you simply just need high resolution. And on the other hand, you have also cheap nonlinearities. So you can afford to change material parameters as a function of let's say, porosity or accumulated strain, and update these values every single time step. Okay, and then now I will show some results. So this is a very simple 3-layer setup. We have here, you can see in the middle, we have a reservoir layer where we are injecting some fluids, and we have a low permeability cap rock and a low permeability base rock. And we have fixed boundaries on 3 sides. On top, we have a free surface. And what happens as we start to inject? Locally, we induce deformation, we induce uplift above the injection site. And as time progresses, at first, simply what we see is just the magnitudes increase. So the uplift domain gets a bit wider, stresses and local strains increase in the reservoir layer. We start to see some changes in the effective pressure field. And then after a little while, we start to see very interesting patterns. And what's interesting here is that we see a high stress layer at the interface of the cap and base layer versus the reservoir. And this is because we inject in this reservoir layer fluids. It wants to expand, and it wants to expand uniformly. But the layers on top and below, they are happy the way they are. Like fluid pressure conditions didn't change there. So they don't want to expand. And then this would result at producing interfacial shear stresses. So there will be shear deformation at the interface, which will then generate slowly uniform stresses in the entire reservoir layer. Like you can see here, now we have already uniform stresses in the entire reservoir. And if we keep injecting, then over some time, we start to see localized deformation. And this is when we already reached high enough stresses and high enough fluid pressure to start fracturing. And we start out with, in this particular case, we start out with the standard Mohr-Coulomb fracturing. You can see as we inject even more, we get a larger yielding domain. And in the end, we get a very nice failure pattern. So in this case, this would be equivalent of having a thrusting in the reservoir formation. And if we continue injecting, then we increase the fluid pressure even more, and we can get to the tensile cap, and we start to form mode 1 open mode fracture. And this will develop into a sill-like structure over time. Yes, and this is the final state. So essentially, you see here the effect of induced seismicity due to fluid injection. But I should point out that I wanted to produce some dynamic figures. So this is not something that would happen at most industrial sites. This is something you want to avoid. I just wanted to show you something exciting. So I chose injection parameters and reservoir parameters such a way that you will see a very dramatic image. So once again, this is not something that we expect. All responsible operators will be able to avoid situations like you see here. What I would like to point out is that often what we use is this standard Mohr circle diagram, that we increase fluid pressure due to injection, here in this one. We increase fluid pressure due to injection, and then we just simply move horizontally the Mohr circle. But this is actually not what I have seen in my models, and I ran many other models, not only this one. Usually I see also there is a change in the radius of the Mohr circle. And depending on if you have depletion or injection, and also depending on the initial stress state, in some cases it might be a stress decrease, decreasing radius, but in most cases for me, I have seen stress increase. So this means actually it's rather challenging to first hit the yield here at the tensile limit. At least in my simulations, most of the time I start with the more Coulomb limit. Yes, so this is just one more example that while it's very useful to use this simple analysis, often when you do the full coupled problem in 2D or 3D, you can find effects that you wouldn't expect to see based on the simple analysis. This is one more result. Now it's slightly more complex geometry. So I took this cartoon and I found a description of a model of a synthetic reservoir sequence, which would be more or less representative of this cartoon. And I implemented that in our code. And here I just show you the final image. After long injection, what I see is that since it is a sealing fault, only the targeted reservoir and only the left side of the fault is pressurized. And since that layer is pressurized, the other layer is not pressurized, we have differential uplift. So left to the fault, we have uplift due to the pressurization. Right side of the fault, we have no uplift. And because of this, we have differential deformation, differential uplift on this pre-existing weak surface, which can generate large shear stresses that would reactivate this fault. And here you can see clusters of microseismicity. One cluster next to the injection point where you have this kind of focal mechanism, and there is a cluster of seismicity on the fault itself, which is reactivated, and there you have this shear sense micro focal mechanism. Yes. So I could stop now, or maybe in 2 minutes show a few nice pictures.
I think you can go for 2 more minutes. That's all right.
Okay. Yes. Thank you. So this is not exactly this is pure fluid mechanics, but this is in a way our plan for the future. For now, we only use the single fluid phase, and now we are working on having multiple immiscible fluid phases in one simulation. So this could be very applicable for EOR, enhanced oil recovery, or CCS, where depending on the conditions, it's very likely that CO2 and water would not form a mixed phase, but they would behave in a way like oil and water. Yes, but this is work in progress. So far, there is no mechanics in this picture, but hopefully in a year or two we will have. And then I would like just to illustrate that actually hydromechanical fracturing due to fluid pressure is not something that is unique for reservoirs, for sedimentary reservoirs. You can also have it in magmatic systems. So here you would have a magma chamber with high fluid pressure. So in this case, the fluid is magma with slightly different parameters than water, but the basic physics is still the same. And due to tectonic extension, as stresses build up, you see the development of a dike-like structure that connects the magma chamber to the surface. And in this case, I will just show some nice fracture patterns. In this case, we can have a magma chamber, and the magma chamber will cool. Due to cooling, it will shrink, And due to the volume change of the shrinkage, we will generate stresses in the rock that will fracture the surroundings. So this is an example of thermal cracking. And you see here nice failure pattern, very similar to a tunnel collapse kind of seismicity pattern. Sorry, fracture pattern. And yes, with this, I would like to thank you for your attention.